Well, hello, class. Thanks for stopping by and joining me. This is the chapter through preview test, and it's long. I think it's like 6 pages. The point is this is to give you kind of an overview of the types of things that I think would be appropriate questions at this point for a test. Some of the items are from previous chapters, of course. Some of the items are from our current chapter. So the first question asks us to simplify some expressions. These are all monomials, meaning that I don't have multiple terms. They're just single terms. I do have some powers like positive exponents, negative exponents, powers, raised to powers, products of powers. So if you're wanting kind of a big overview of this topic, you can look up, I think, laws of exponents. You can find some things. But let's begin. Let's start with the first of the first, part A. And in this, I see two things, right? I see the numerical coefficients, and then I see these variables x. If I was to look at the numerical coefficients, clearly we've got 6 over 18, right? And 18 has a factor of 6 in it. In fact, I could rewrite this as 6 over 3 times 6. So I can see that there is a 1 lurking inside of there. So I'm left with this factor of 3 in the denominator. It's important. Where is it? It's in the denominator. The other thing that I see happening is this negative exponent, and I can pretty quickly get rid of those by multiplying by the number 1. This is the number 1 I'm choosing to multiply by, and the reason why I selected that is when I multiply by this version of 1, x to the negative second power times x to the positive second power becomes x to the 0 power, and x to the 0 power equals 1. So you can see what happens is these two factors of x, right? X to the negative second, they were in the denominator. They jump into the numerator. So my numerator now has 5 factors of x, right? 1, 2, 3, 4, 5. So my answer is going to be x to the 5th power in the numerator. And in my denominator, I'm just going to have just the factor 3. So this is the answer to A. B. So I'm going to multiply some things here. Well, first, let's square this. Right, you can see that I've got this is being raised to the second power. So that means I have to square that thing in parentheses. To square it means I'm multiplying it by itself. And because there's just two of them, I could reasonably write that out, right? This is 3x squared times another 3x squared. If this was to the 10th power, I would not do this, but I can do this. 3 times 3 is 9. And x squared times x squared, right? When I multiply those, I end up with 4 factors of x. So that's 1, 2, 3, 4. It becomes 9x to the 4th power. And I'm going to multiply that by a factor of 2 and another factor of x. 9 times 2 is 18. And x to the 4th power times x to the 1st power is going to be x to the 5th power. So there we go for part B. Part C has a numerical coefficient of 7, and then I'm multiplying that times x to the negative 5th. I'm going to conceptually get rid of that by multiplying by a number 1. Oops, that's not the number 1. This is the number 1. Same thing in the numerator and denominator. I point out to myself that, hey, this is, when I multiply it with this, is going to be x to the 0 power, which is 1. So that's why I picked to multiply both the numerator and denominator by x to the 5th. So in my numerator, I'm left with a 7, and the denominator is just x to the 5th power. Part C, if I multiply, oops, get out of the way. If I multiply a to the negative second times a to the second, this times this, I'm going to get a to the 3rd power times another a to the 3rd power, right? And then over 3 to the negative 1st. I'm just going to multiply the top and bottom by 3 to the 1st. So this is now just the number 1. Same argument as always. In the numerator, I have 6 factors of a times a. So I've got a to the 6th power, and then I'm multiplying that by 3. So 3a to the 6th power. So for f, in my numerator, the first thing I'm drawn to is the fact that I've got 3 times 2. When I multiply that, that's 6, and in my denominator I already had a 6. So I can see I've got no numerical coefficients. In my numerator, I did have 4 factors of x times another factor of x, so that will be x to the 5th power. And then the denominator, I had x to the negative 3rd. To get rid of that negative exponent, I'm just going to multiply by 1. So I'm going to go x cubed in both the numerator and denominator. And when I multiply these two, I get x to the 0, which equals 1. So my answer is just going to be x raised to the 8th power. I have 8 factors of x here. And that was f. And I realize now that I skipped way back over here, part E. So let's go back and look at part E. In part E, I don't like raising something to the negative 2nd power in the numerator. That's the possibility of me making a mistake is good. So I'm going to rewrite this as 4x to the 5th, and I'm going to square that, and I'm going to multiply by 4x to the 5th. Of course I can do that, because what I'm multiplying by is the number 1. When I do that, I happen to make a number 1, right? This, and this together are something to the 0 power. Doesn't matter what it is to the 0 power, it equals 1. So my numerator contains the number 1. The denominator has a factor of x. And I also have 2 of these. Now, I can write this out twice, but I can also go through and square each of the individual factors that I have. So if I were to square the 4, that would give me 16. And if I square x to the 5th, that would be x to the 10th. So that's a nice shortcut, right? I can do that. But just to convince myself that I didn't make that up, I am going to go ahead and write it out as 4x to the 5th times 4x to the 5th. I can see 4 times 4 is the 16. X to the 5th, x to the 5th is x to the 10th. So yeah, it was good. I'll write it here, 16x to the 10th. And then one final thing, I've got a factor of x times 10 more factor of x, which would be 11. So I'll write this as 1 over 16 times x to the 11th power. And that was part E. We are on to the second page, and it has, I think, 6 equations. These are not particularly difficult, right? I think we consider this to be a checkpoint, and we're looking for mastery at this point. There's a couple things that I want to make sure you're reminded of in terms of whether or not an equation solution set is all real numbers or if there's no solution at all. So just be aware that's going to pop up in these 6. Let's start with A. So in A, I'm going to begin by rewriting the left-hand side. And I'm going to rewrite the left-hand side using the distributive property. So this first chunk I can rewrite as 6 times x. That's 3 times 2 minus 15. And then I can write minus 2x plus 2 and then plus 5. And over on the other side that equals 12. So what I'm claiming is that this negative 2x plus 2 is the same as the thing that was above here, right? And I'm also claiming that this 6 times x minus 15 is the same as 3 times the quantity of 2x minus 5. So when you look at it, you can see, yes, one of the ways we can do this is, multiplying the binomial. I have a monomial times a binomial. This is the simplest form of the distributive property, so I didn't require an area model here. Let's collect up like terms. I've got 6 times x minus 2 times x, which is going to give me 4x. And then I have a negative 15 plus 5, I'll put it with 5, is negative 10. And negative 10 plus 2 would be a negative 8, and that is 12. Therefore, 4x is 20 and x is 5. Every step of the way, I can tell you exactly a justification for what I did, right? From rewriting to collecting like terms to the addition property of equality to the division property of equality. So x is 5 for A. Let's move on to B. In B, same thing. I'm going to go ahead and use the distributive property and rewrite the left-hand side as negative 2x plus 6 minus 4x, and that's going to equal negative 8x plus 14. These together make negative 6, so I have negative 6 times x plus the number 6 is negative 8x plus 14. If I add 8x to both sides, this is going to become negative 6x plus 8x will be 2x plus 6. And over here, if I add 8x, it's just going to be 14. Taking away, let's see, taking away 6 from both sides is going to give me 8. So 2x is 8 divided by 2, x is the number 4. If you're at all suspicious, right, a good strategy is to always plug this number back into the original equation and make sure you get the right thing, just to show you that it's not too much of a burden to do that. If I put the number 4 into this first set of parentheses, 4 minus 3 is 1, so I'm left with a negative 2. If I put a 4 here, this is going to be negative 16. Those two together would make negative 18. And then on the other side, if I put a 4 here, that's going to give me negative 32 plus 14. So if I have 32 and I subtract 14 from it, I do get negative 18. So of course, an important and a big idea is that once you find a solution to an equation, you're literally finding the values of the variable that make the statement true, both the left and right hand side the same. All right, let's move on to the next problem. That's super quick. I'm going to add 3x to both sides. I notice these are not the same. When I add 3x to both sides, right, this side just becomes 22, and the other side becomes 6x minus 2. If I add 2 to both sides, we get that 6 times x is 24. And 4 times 24 is 24 divided by 6 is, what is that, 12? 6 times 4. Yeah, this is 4. So in part D, I do have an x on both sides. And if I subtract x from each side, on the one side I have a negative 2 plus 10. On the other side I'm going to have an 8. When I combine negative 2 and 10, I end up with 8. So this collapses to this statement, 8 equals 8. When that happens, what's essentially happened is any real number would work. It doesn't matter what I picked for x in the original equation, it would be a solution. So when we see this, we just say our answer is all real numbers. Any value that I could plug in for x would make 8 become 8. Another way of thinking about this is if I look at these as equations of lines that are simplified, this line right here has a y-intercept of 8 and a slope of 1. This, when I simplify by adding the negative 2 and 10, also has a y-intercept of 8 and a slope of 1. So if I think about the left and right hand side as lines, these are two lines that are parallel and they have the same y-intercept. So basically any value of x would make both sides the same. Let's move on to Dbcde. For E, I'm going to begin by rewriting a portion of the right hand side as 12x. 3 times 7 is negative 21 and then plus 1. And then over here I've got 12x plus 15. Oh, these are indeed the same. So if I take away 12x from each side, I'm just going to get the statement 15 is equal to negative 21 plus 1, negative 20. Well, there's no magic that's going to make this true, right? 15 is not the same thing as negative 20. And there's no variable left in this expression, so I can't find value of x that would make this true because it's gone. So in this situation, right, when we get a contradiction, something that we know is not true, we would say no solution. Another way of thinking about this in terms of lines, if I looked at this equation and the simplified version of this one, the other side would be 12x minus 20. These are two lines. If I graph the left and the right hand side, they're both lines with slope 12, up 12 units over 1. One of them has a y-intercept of 15, and the other one has a y-intercept of negative 20. So what these are, the left and the right hand side end up being parallel lines. And there's no way that we're ever going to get a pair of parallel lines to intersect each other. So that's another solid reason why we're saying there's no solution. And then finally for F, same deal. I'm going to begin with rewriting the right-hand side using the simplest form of the distributive property. This will become 4x minus 12. If I combine my 4x's, that is 8x, positive 6 and negative 12 would be a negative 6. And I can already see what's happening. This is just like the problem above it. I have the left and right hand side, if I think about them as lines, they're both y equals 8x minus 6. Both of them have slopes of 8, and they both have y-intercepts that are exactly identical at negative 6. So we would say that they are parallel lines because they have the same slope. Ooh, that was loud. They are parallel lines, they have the same slope, but they also have the same y-intercept. So these two lines coincide with each other. If I wanted to, I could take away 8 from both sides, or 8x from both sides. I would get that negative 6 is negative 6. That statement is always true. So what we have here is evidence that any value of x would work. So we would just say, again, all real numbers. Okay, we are on to the third page, the third problem. I think there's a total of 1, 2, 3, 4, 5, 6, 7 equations here. These are a little bit more robust, and we're looking at the tools that we developed and discussed in this chapter, namely looking inside, undoing, and rewriting. This first equation, well, and that's another tool too, is fraction busters. That came a lesson later. This first problem, I'm going to use fraction busters to get rid of my fractions. When I look across at my denominators, I can see I have a factor of x. I have a factor of 3. There's an x, there's a 3, and there's a 2. So those three factors, x, 3, and 2, will take care of everything I see in my denominator. So what I'm going to do is, visually at least, I'm going to place those factors in each one of the numerators. These numerators are just simple monomials, right? So I'm just going to, visually just multiply each one of them by that. Because you're here and you're like, hey, I need help, let me go ahead and I'll write that out. So this is going to become a 1 times x times 3, whoops, times 2. So that's the first one over x, plus I've got a 4 times x times 3 times 2 over 3. And then that equals 3 times x times 3 times 2. And that's all over 2x. So if we look real carefully, right, this got a factor of x times 3 times 2. This got x3 2, and this one got x3 2. So all of them got copies of the factors x times 3 times 2. So that's an important thing to point out, because if these equations, if this equality is true, I only preserve that equality statement by, in this case, multiplying both sides by the same factors. So I'm multiplying both sides by 6 times x, essentially. So what's nice is now I can see clearly there are some 1s. So this is a 1, it's gone. This is a 1. It's gone. The 2 and the 2 form a 1, and the x form a 1. So you can see exactly what I'm left with. This equation becomes 6 plus 8x equals 9. And I probably would write that almost on the very first step after I wrote down what I was multiplying by. And I can usually get that right. I'm going to take away 6 from each side. So this is going to become 8 times x is equal to 9 minus 6 is 3. And then as a final step, I'm going to go ahead and divide both sides by 8. And when I do that, I get x is 3/8. Now that is a fabulous number. It's a nice number that you could take and you could enter it in your calculator, and then you could plug that in to the original equation and verify that it does make the left and right hand side the same. Okay, definitely rewriting is going to happen with this problem. I need to rewrite the 25 and the 1/5 so that they look like they're the same base. When I see 25 and I see 1/5, I immediately think about a base of 5. And something that I discussed in class was sometimes it's beneficial to just write down a few samples of powers of 5. So I can start with 5 to the 0 power, 5 to the first, 5 to the second, 5 to the third. And if I was going backwards, I could write 5 to the -1, 5 to the -2. Anything raised to the 0 power is the number 1. So this is 1. And as I move forward, I'm multiplying times 5. 1 times 5 is 5. 5 times 5 is 25. 25 times 5 is 125, right? So those are powers of 5 as my exponents increase. If my exponents are decreasing, I'm dividing by 5. So 125 divided by 5 is 25. 25 divided by 5 is 5. 5 divided by 5 is 1. 1 divided by 5 is 1/5, which is a nice insight into negative exponents not being negative numbers. Negative exponents are not negative numbers. Negative exponents are fractions. Well, depending, I guess, on what the base is. This one's going to become 1 over 1/25, right? So the two values that I want to use are the 1/5, so I'm going to be using 5 to the -1st, and 25, which is 5 to the 2nd. So my strategy here is to rewrite this so that I have those same bases. So 25 is 5 squared, and then I'm raising that still to the 3x minus 1 power. On the other side, I've got 1/5, which is 5 to the -1st power, and I am raising that to the x plus 4 power. So when I raise a power to another power, a power raised to a power, the shortcut is I multiply the power times the new power. So this is going to become 5 to the 2 times 3x minus 1. I'm multiplying 2 times 3x minus 1. And when I multiply 2 times 3x minus 1, I get 6x minus 2. Right? Make sure that we see that the 2 is multiplied both by the 3x and the -1. On the other side, this is going to be 5 to the, guess it, what is it? Yes, you are correct, -x and then minus 4. Now that my bases are the same, they're both the number 5, the only way this statement can be true is if 6 times x minus 2 is the same as -x minus 4. So I'm going to set those powers equal to each other, right? 6x minus 2 has to be the same as the opposite of x minus 4. Therefore, if I add an x to both sides, I get 7x minus 2 is -4. Add 2 to both sides, I'm going to get 7x is -2, and therefore x would be -2 over 7. Now, you can check this answer one of two ways. If a solid approach is to check it in the very original equation. So if you had 25 and use your TI-84 calculator and raise that to the open parens 3 times -2/7 minus 1,
and just verify that you get the same thing on the right hand side. It's good. An okay way to check too is to just maybe plug into this version, but then that's assuming we didn't make any mistakes up at the beginning, and my assumption is that I'm always making mistakes, so that's why I would plug it into the original equation to check. Last one here, another approach. By the way, we called this was rewriting, right? We were rewriting parts of it so the bases became the same, but then we're also calling this kind of looking inside, because I'm looking at what the exponents are and I'm saying, well, those exponents have to be the same. Over here, I call this looking inside because I know that this exponent, the thing that lives inside of the radical, that must be the number 81. And the reason why is because I know that just the basic number fact that the square root of 81 is 9. So I would say, hey, 4x plus 1 must be the number 81. If I take away 1 from both sides, 4x must be the number 80. And then division property of equality, x must be 40, 20. X must be 20. So that's C. All right, let's move on to, oh, isn't D lovely? Look at D.